Welcome back. Today we're going to be working on 13D, which is adding and subtracting scientific notation. Our content objective is students will be able to perform operations expressed in scientific notation and standard notation. Language objective is students will be able to discuss how adding and subtracting expression compares to combining like terms. And why am I learning this? Well, it's important for real-world problems like finding distances between planets. So remember our central question. I want you to think throughout the entire lesson, how are we using the property of exponents to simplify expressions? Are we adding exponents? Are we subtracting exponents? And why exactly are we doing that? Okay, so background knowledge. Just to quickly remember, our coefficient has to be between 1 and 10. Scientific notation is a nice compact way of showing very large or very small quantities. So here are some examples. This large number was expressed as 6.32 times 10 to the ninth, and this rather small number was expressed as 2.7 times 10 to the negative fifth. It allows me to quickly assess how big or smaller a number is without having to count how many zeros there are and try to find the place value and whatnot. Okay, so in the previous lessons, we've worked with multiplying scientific notation. We've worked with dividing. So now we're going to be moving on to adding and subtracting. So let's first go off of things that we do know. If I gave you 5x cubed plus 7x cubed, you would simplify that and say, okay, that is 12x cubed. So notice all we did was combine the coefficients. We didn't combine the x cubed and all of a sudden make it x to the 6th. So keep that in mind. So again, we just combined the coefficients of 5 and 7, but we kept x cubed the same. Okay, so what about this case? Is it any different? No. Okay, the same way we're going to break up 5x cubed as 5 times x cubed, we can break up 5 times 10 cubed as 5 times 10 cubed. 7x cubed would be 7 times x cubed, and 7 times x cubed would be 7 times x cubed, so same thing. So in the same way that all I did was combine the coefficients here, that's exactly what I'm going to do here. I'm going to combine the coefficients, but I'm going to keep the base the same. So essentially what happened was I added the 5 and I added the 7 to give me 12, but notice the base 10 cubed stayed exactly the same. I didn't add the exponents and call it 10 to the 6th. That's not it, because we're not multiplying the tenths together. Okay, so again, we just broke up 5 and 7, combined them to give us a 12, so this would be our answer. Now, if the bases are the same and the exponents are the same, you are allowed to follow the rules of adding expressions. So in other words, combining like terms. So that's what I'm really going to stress about today, is making sure that you have the same base and the same exponent. Okay, so let's understand a generic form for adding numbers written in scientific notation is basically you got to make sure the base and the exponents are the same. And once you do that, all you're doing is adding the coefficients. That's it. You're going to keep the same base. You're going to keep the same exponent. That doesn't change. So can't stress this enough. Make sure your base and make sure the exponents are exactly the same. That's the only way to do it. And you can kind of even correlate that to when we add and subtract fractions. Before you can add and subtract fractions, you need the same denominator. So you can kind of make that connection as well, if that helps. So in a case like this, it says find the sum of the following. Make sure your answer is in scientific notation. So first what we're going to do is check, do we have the same base? Do we have the same exponent? Same base raised to the same exponent is a better way to phrase it. We have 10 cubed here. We have 10 cubed here. So yes, because of that, I can go ahead and combine the coefficients together. So I'm going to go ahead and combine 5.2 plus 3, and I'm just going to multiply that by 10 cubed. So 5.2 plus 3 is 8.2, so we're going to have 8.2 times 10 cubed. So notice yet again, I am not combining the exponents at all. I'm just keeping it the same. Same base raised to the same exact exponent, kind of like denominator. If you don't add the denominators together, you keep the same denominator. Okay. Okay, so let's take a look at this one. Again, I'm going to check, do I have the same base raised to the same exponent? Well, we have 10 to the negative second, 10 to the negative second, so we're good. All I'm going to have to do is add the coefficients. I'm going to add 4.1 with 3.4, and I'm going to go ahead and multiply it by 10 to the negative second. So again, I'm just keeping that base raised to the same exponent. That's not going to change. 4.1 plus 3.4 is 7.5, so I'm going to have my answer as 7.5 times 10 to the negative second. Now, I forgot to mention this in the previous example. I should be checking to make sure the coefficient is between 1 and 10. This one was, so that's why it's okay. Same thing here, it is between 1 and 10, so that would be my answer. Okay, let's check the last one here. We have 10 to the 14, 10 to the 14. Since they are the same base, same exponent, I can go ahead and just add the coefficients together. So I'm going to go ahead and add 1.62 plus 7.07, and I'm going to multiply that by 10 to the 14th. So all I have to do here is add the two numbers together, which is going to leave me with 8.69 times 10 to the 14th. My coefficient is within the correct range of between 1 and 10, so that is my final answer, 8.69 times 10 to the 14th. So please make sure that when you're adding scientific notation, you're making sure that the base and the exponents are the same. It has to be the same base raised to the same exact exponent before you can start adding the coefficients together. Okay, so let's go ahead and take a look at something that we know again. So now we're going to move from addition to subtraction. Here, 17w to the ninth power minus 9w to the ninth. We're going to go ahead and say it's 8w to the ninth, and all that really happened was you subtracted the coefficients, because w to the ninth is the type of variable, so it's going to stay the same. So it's saying that we have 17 w's to the ninth and negative 9 w's to the ninth, so altogether you would have the 8w to the ninth. So same thing here, I'm going to break it up to 17 times w to the ninth, 17 times 10 to the ninth, etc., just to kind of show you. So my answer for this one would be, well, since the base and the exponents are the same, I'm just going to go ahead and subtract the coefficients. 17 minus 9 is 8, so that's going to be 8 times 10 to the ninth power. Now, if you're wondering how I did that, again, all I did was subtract the coefficients, so 17 minus 9, but I'm still raising it to the same base, to the same exponent, okay? So a way you can think of it as well is saying I have 17 of them of the 10 to the ninth, and I have 9 of them raised to 10 to the ninth. So if I have to subtract those, I would only be left with 8 10 to the ninth. So again, I'm going to say this over and over throughout this entire lesson. Make sure the base and the exponents are the same. So once you have that, you can go ahead and just treat them as if you're combining like terms. Okay, so the generic form for subtracting numbers written in scientific notation is very similar to adding, except instead of adding, we're subtracting. So whenever your base and your exponents are the same, all you're going to simply do is subtract the coefficients, but keep the same base and keep the same exponent. So just remember, the bases and the exponents must be the same, okay, before you start adding the coefficients or before you start subtracting the coefficients. So here, let's go ahead and practice some subtraction. Here, since the base and the exponents are the same, I can go ahead and just subtract the coefficient. So here I'm going to set it up as 5.2 minus 3 times 10 to the third power. So I'm just keeping the base, keeping the exponent. 5.2 minus 3, I'm going to have to do some side work real quick. 5.2. I want you to remember 3 written as a decimal. The decimal belongs behind the 3, so I'm going to line up the decimals. And that's going to leave me with 2.2. So I'm going to leave with an answer of 2.2 times 10 cubed. I'm going to check that my coefficient is between 1 and 10, which it is, so that is my answer, 2.2 times 10 cubed. Now let's take a look at another example. Once again, we have the same base raised to the same exponent, so all I would have to do is work with the coefficient. It is a subtraction problem, so I'm going to subtract the exponents. Sorry, not exponents, coefficient. So I'm going to put 9.89 minus 7.92 times 10 to the 14th. So here I'm going to do some side work. I'm going to make sure I'm going to line up my decimals. And I'm just going to subtract 9 minus 2 is 7, 8 minus 9, I'm going to have to borrow. And 8 minus 7 is 1. Bringing on that decimal, I'm left with 1.97 times 10 to the 14th. My coefficient is within the correct range of between 1 and 10, so I'm going to go ahead and say my answer is 1.97 times 10 to the 14th power. So let's try one last example for this part. We have the same base raised to the same exponent in both problems, so I can go ahead and subtract the coefficient. So I'm going to put 7.4 minus 6.6 times 10 to the negative fifth. So once again, notice I'm not doing anything to the powers. I'm just keeping the same base, keeping the same exponent. I'm going to do some side work. I'm going to do 7.4 minus 6.6. This is going to become 14. Borrowed. 14 minus 6 is 8. Bring that decimal down. 6 minus 6 is 0. So I'm left with 0.8 times 10 to the negative fifth. So real quick, I'm going to check if my coefficient falls within 1 and 10. Unfortunately, it doesn't. It's too small. So what do I do because it's not in scientific notation? Well, just like before, we're going to adjust it. This needs to be bigger, so I'm going to multiply it by 10 to the first, which means I'm going to have to multiply this side by 10 to the negative first. And again, why does this work? 10 to the first times 10 to the negative first is 10 to the 0, which is just 1. Multiplying anything by 1 doesn't change the value of that expression, so it's okay for me to do that. So by doing that, I'm moving my decimal once over to the right, leaving me with 8 times 10 to the negative 5 plus a negative 1, which gives me a negative 6. So now I can go ahead and say that that's my final answer because my coefficient does fall in the correct range between 1 and 10. Okay, so let's take a look at this one. I'm going to check, is my base raised to the exponents the same? In this case, it's not. So what do? Well, we need to adjust it so we can make that happen. So here, there's going to be two options. You can either turn both of them into a 4, or you can turn both of them into a 3. I'm actually going to show you both methods to kind of see what happens. So like I said, on one hand, we can go ahead and turn both into a power of 4, and then on the other hand, we can turn both into the power of 3. So let's go ahead and try on one side, converting both into a power of 4 and see what happens. So if I wanted to turn both into a power of 4, I am going to just keep 7.1 times 10 to the 4th minus, now this is going to have to change. In order to make this 10 to the 4th power, I'm going to have to multiply this by 10 to the 1st. So to adjust this, I would have to multiply this by 10 to the negative 1st, which will move the decimal once over to the left. So now I'm going to have 0.34 times 10 to the 4th. Now that I have the same base and the same exponent, I can go ahead and combine the coefficients. So I'm going to do 7.1 minus 0.34 times 10 to the 4th. Just need to go ahead and subtract. I'm going to use some side work here. 7.1 minus 0.34. Please make sure whenever you're adding or subtracting decimals that you do line them up. It's important that you do that. So here, can 0 minus 4? No, so I'm going to go ahead and borrow. 10 minus 4 is 6. I'm going to have to borrow once more. 10 minus 3 is 7. And 6 minus nothing is 6. So I'm left with 6.76 times 10 to the 4th. And here it's already good because the coefficient is between 1 and 10. So this is my final answer. Let's try that again. Now let's take a look at the other option. As we're checking out the other option, I want you to keep in mind the different steps and which one you may prefer to do in the future. Okay, so this one, let's go ahead and turn both into a power of 3. So I'm going to go ahead and change the first one because I want to make it into the third power. So I'm going to have to multiply this by 10 to the negative 1, which would require me to multiply this by 10 to the positive 1. So this is going to move my decimal once over to make it larger, leaving me with 71 times 10 to the third power. Since 4 minus 1 is 3, I'm going to subtract, I'm going to keep this the same, 3.4 times 10 cubed. Now that my base and my exponents are the same, I can go ahead and combine the coefficients. So I'm going to do 71 minus 3.4 times 10 cubed. I'm going to do some side work real quick. We're going to do 71, decimal belongs at the end, and subtract that from 3.4. Go ahead and add an extra 0. 0 minus 4, you can't do that. You're going to have to borrow. 10 minus 4 is 6. You're going to have to borrow once more. 10 minus 3 is 7. 6 minus nothing is 6. So in this case, I have 67.6 times 10 cubed. Now I'm not done because this coefficient is too large, so I'm going to have to adjust it. And in order to do that, I'm going to have to multiply by 10 to the negative first. And here I'm going to have to multiply by 10 to the positive 1 to balance things out, leaving me with 6.76 times 10 to the fourth. So what I want you to see from this is no matter which way you solve it, you're going to have the same answer. However, something with practice is you're going to realize whenever you choose the smaller exponents, almost always you're going to have to adjust the final coefficient. Now, if you choose the larger exponents, there's a good chance you're not going to have to. So whenever you have the choice, should I pick the larger exponent or the smaller exponent, it might be a better choice for you to go ahead and choose the larger exponent because you most likely won't, I'm not going to say always, but you won't always have to adjust the coefficient. Okay, so let's go ahead and try number 8 here. We have a choice. We can either turn both exponents to a negative 2 or both to a negative 1 because they don't match already. I am going to pick the larger exponent, which is a negative 1. So in order to do that, I'm going to go ahead and multiply this by a positive 1 to make it match. And by doing that, I'm going to have to even things out by multiplying this by 10 to the negative 1. Moving my decimal over once, I'm going to be left with 0.12 times 10 to the negative first, because negative 2 plus 1 is negative 1, plus 2.5 times 10 to the negative first power. Now that my base and exponents match up, I can go ahead and combine like terms. So I'm going to add 0.12 plus 2.5, and I'm still going to have it multiplied by 10 to the negative first power. I'm just going to add this, leaving us with 2.62 times 10 to the negative first. Now, this is done because my coefficient does fall within the correct range of between 1 and 10, so I'm done. But again, if you wanted to, you could have chose to turn both of them into a negative 2, which would still give you the same answer, but you would just have to make sure your final coefficient is adjusted to make sure it falls between the range of 1 and 10. Okay, so here would have been the other choice right here, and that would have given you 26.2 times 10 to the negative second. You would adjust it. So again, it's that extra step versus just having that one final answer. Okay, number 9, same idea. Do I want to turn both into negative 1s or both into negative 2s since they're not already the same? Hopefully you want to choose the negative 1. So I'm going to go ahead and change this by multiplying it by 10 to the positive 1, which will require me to multiply this by 10 to the negative 1 to balance things out. That would move the decimal once over to the left, which is going to leave me with 2.5 times 10 to the negative first minus 0.12 times 10 to the negative first. And now that the bases and the exponents match up, I can go ahead and combine like terms. So in this case, I'm going to go ahead and subtract the coefficients, but still multiply it by 10 to the negative first power. I am going to do some side work. 2.5 minus 0.12. Notice again, I'm lining up my decimals. I'm going to subtract. 10 minus 2 is 8. 4 minus 1 is 3. Bring down 2. I'm left with 2 and 3/800 times 10 to the negative first. I am done because the coefficient does fall between 1 and 10, so we're good to go. But again, here are the different options. This was my first option here, which led me straight to the answer. But if you chose to convert both into negative 2's, you should have ended up with something like this. You got an answer where the coefficient was too large. You'd have to adjust it. But once again, you'd get the same answer. So it really doesn't matter which method you choose. Just keep in mind that if you choose the larger exponent, there's a good chance you're not going to have to adjust the coefficient. Okay, so we're going to go ahead and try the next 3 problems on your own. So go ahead and pause it and let's see how well we do. Okay, so I'm just going to quickly go over the answers, and then after I go over the answers, I'll go ahead and go step by step into the steps of how I got the answer that I did. Number 10, the answer is 5.08 times 10 to the negative fifth. Number 11 is 6.75 times 10 to the fifth. And number 12 is 5.7014 times 10 squared. Now let's go ahead and look into detail how we got those answers. So again, you're going to want to choose to get both of the exponents to be the same. I'm going to always choose the larger exponent because I don't want to have to adjust the coefficient at the end. So negative 5 is bigger than negative 6, so I'm going to adjust this by multiplying it by 10 to the positive 1. It only needs to be changed by 1, so this is going to be multiplied by 10 to the negative 1, moving decimal once over. So I'm going to be left with 5.3 times 10 to the negative fifth minus 0.22 times 10 to the negative fifth. Now that I do have the same exponent, same base, I can go ahead and combine the coefficients. So 5.3 minus 0.22 times 10 to the negative fifth. I'm going to do some side work. 5.3 minus 0.22, always lining up that decimal. Of 805, so my answer is 5.08 times 10 to the negative fifth. Okay, what about number 11? Hopefully number 11, you chose to stick with the 10 to the fifth, so you're going to multiply this by 10 to the first. Why to the first? Because you only need to move 4 by 1 to make it a 5. So here you're going to multiply it by 10 to the negative first to balance things out, moving this over 1 to the left. I'm left with 7.2 times 10 to the fifth minus 0.45 times 10 to the fifth as well, because 4 plus 1 is 5. At this point, the base and the exponents match up, so I'm going to combine like terms. 7.2 minus 0.45 times 10 to the fifth power. I'm going to do some side work. 7.2 minus 0.45. We're going to have to borrow. And that's going to leave us with 6.75 times 10 to the fifth. And again, we're done because the coefficient does fall between 1 and 10. Now, if you take a look at number 12, number 12's a little tricky. Why? Well, first, do you want to turn both exponents to a 2 or to a negative 1? Hopefully you said 2. Now, for a second, let's think, how do you get negative 1 to become a 2? First of all, you're definitely going to add, but how much are you going to add? Well, hopefully your answer is you're going to add 3. Okay, why? Let me clarify. 3 minus 1 is 2. So that's what I need it to do. So for that reason, I'm going to have to then multiply this part by 10 to the negative third. So this is the first time it's ever happened where we're multiplying anything more than a negative 1 or a positive 1, and this is why. So here I'm going to move my decimal over 3 spaces to the left, so 1, 2, 3. So I'm left with 5.7 times 10 squared plus 0.0014 times 10 squared. Now that the bases and exponents match up, I can go ahead and combine like terms, adding those coefficients together. 5.7 plus 0.0014 times 10 squared. I'm just going to add these two numbers together, leaving me with 5.7014 times 10 squared. Since this coefficient does fall between 1 and 10, I am done, and that is my answer. Okay, so now, what do we do when they're both not in scientific notation? We have one in standard, one in scientific notation. What are we going to do? Just like in the previous lesson, it's always easier to convert both into scientific notation because it's a nice, compact way of representing a number. Keeps things nice and neat. So I'm going to go ahead and do that. But as I'm doing that, I'm going to keep in mind I want to keep the power of the larger exponent. So right now, if I were to convert this into an exponent, it would be 5.7 times 10 to the, let's see, 5.7 is going to be 1, 2, 3, 4, 5. Okay, because of that, I'm going to go ahead and adjust this one by 1 to make it 10 to the 5th as well. So I'm going to multiply this by 10 to the 1st, which means I'm going to have to multiply this by 10 to the negative 1st, moving it once to the left. So now I have 0.472 times 10 to the 5th plus 5.7 times 10 to the 5th. Now that we have the same base raised to the same exponent, I can go ahead and combine the coefficients together, leaving me with 0.472 plus 5.7 times 10 to the 5th. This I can go ahead and do in my head, but I definitely encourage you to actually show your work. I'm going to be left with 6.172 times 10 to the 5th power. Okay, but again, I would want you to actually show your work in your homeworks, 5.7, lining up those decimals, and actually showing the work. This is 2, this is 7, this is 11, this is 6. Still gives us the same answer, but it's important for you to actually show your work. So here, well, let's see, we already have this one in exponential form, but this one here, it would be rewritten as 5.1 times 10 to the, let's see, 1, 2, 3, 4. So it's to the 4th power. So I'm going to go ahead and adjust this one by, since it is smaller, I'm going to go ahead and multiply it by 10 to the 2nd. By doing that, that would bump it to 10 to the 4th, which is what I need. But I'm going to have to balance things out by multiplying this by 10 to the negative 2nd. The decimal always belongs at the end of the whole number, so here moving it 2 spots to the left, I'm going to be left with 1.7. There's no point in writing that 0, it's not going to hurt, but I'm going to go ahead and leave it out, times 10 to the 4th. My bases are the same, and so are the exponents, so all I need to do is go ahead and combine the coefficients. So 5.1 minus 1.7 times 10 to the 4th. Here, subtraction, highly suggest you show your work. 5.1 minus 1.7. We're going to borrow, leaving me with a 4 and 3. So it's going to be 3.4 times 10 to the 4th. So again, it's always in your best interest to try to keep the larger exponent. There's always that good chance that you're not going to have to adjust your coefficient. And that is actually going to conclude the lesson for today. Thank you so much for tuning in. And as always, until next time, bye.